Hey class, this is Mr. Z's. Sorry I couldn't be there. This ELA testing schedule has it all confused up. I can't make it because I'm at the high school. But I'm still going to be here to save us some time and keep us on pace so we can get to our roller coaster build. So today we're going to talk about energy forms and how energy changes from one form to another. So as we discussed, energy is the ability to do work. So this intertwines energy and work. And because of this direct connection between energy and work, energy is also measured in the same units as work, joules. In addition to using energy to do work, objects can gain energy because work is being done on them. Similarly, if an object is doing work, it can lose energy by doing work. Mechanical energy is a term we use in science to define the combination of both kinetic and potential energy. When work is done to an object, the object acquires energy. The energy it acquires is known as mechanical energy. Mechanical energy, we sometimes abbreviate as TME for total mechanical energy, is the sum of an object's kinetic and potential energy, like I just said. And it has the formula this: total mechanical energy is equal to kinetic energy plus potential energy. The law of conservation of energy states that energy cannot be neither created nor destroyed by any ordinary means. And this pretty much means it cannot be created or destroyed. And since it can't be created or destroyed, it can only be converted from one form of energy to another. If energy seems to disappear, then scientists tend to look into what's going on, and it has led to many important discoveries in our history. So often the things that are confusing can lead to better understanding if you take the time to look into it. Here's the main topic of our discussion today is energy conversions. As stated, energy can't be created or destroyed, but it can be changed from one form to another. And the changes in energy from one form of energy to another are called energy conversions. Just like if you would go to the bank and convert all your coins into dollars, it would still be money, but you're converting from coins to paper money. Now let's look at a couple of energy conversions that you might be familiar with. So as we said, all forms of energy can be converted into other forms. Two very popular ones that you should be familiar with are, one, the sun's energy can be converted through the use of solar cells, also known as photoelectric cells, into electricity. So these cells collect energy from the sun's light and turn it into electricity you can use in your house. Another very well-known form of energy conversion is photosynthesis. Green plants collect the sun's energy through their leaves, and it takes the sun's light, and through the process of photosynthesis, it combines it with other things and turns it into starches and sugars, which is also known as chemical energy. Those starches and the sugars are the parts of the plants that we usually eat and give us energy. So here's my question to you, class. What kind of energy conversion is used to make cars move? Let's think about this. What do we have to put in our car to make it move in the first place? Well, that's right, we have to go to the gas station and fill it up with gas. If we don't have gas, our cars won't move. And gas is a sort of fuel, just like food is to us. Food is our fuel. Gas is fuel for cars. And both of the food and fuel are forms of chemical energy. Now, once this fuel enters the engine, there's an explosion that occurs inside of the pistons. And when that explosion occurs, it makes the motor move. But that explosion, like all explosions, releases quite a bit of heat. That heat expands the gases in these chambers, forcing the piston to move away from the cylinder. And at that point, you start creating motion of the car. And as I said before, that motion can be called mechanical energy, because the car can not only increase its speed, but it could also drive up a hill, increasing its potential energy. So a car can convert fuel in the form of chemical energy into heat from explosions into mechanical energy, an increase in potential and kinetic energy, depending on where you're driving. So let's talk about some states of energy. The most common energy conversion is the conversion between potential energy and kinetic energy. Actually, most of you are quite familiar with these conversions. Like if you drop something on the floor. Originally it was in your hand above the ground, which is a measure of its potential energy, how high it is from the ground, and as it fell it sped up before it hit the ground, so that potential energy was converted into kinetic energy. All forms of energy can either be considered potential energy, as in stored energy, or kinetic energy associated with some sort of movement. For example, heat energy. If you've ever seen a campfire, you see these wavy lines above it, or anything that's hot. That's showing you that there's motion associated with that heat. And in fact, the temperature of an object is just a measure of the average kinetic energy of the object's molecules. Potential energy is anything stored. We talked about gravitational potential energy, but we've also talked about elastic potential energy, the type of energy that's stored in rubber bands or springs. And we also have the potential energy that's stored in food, which is not quite energy until you perform a chemical process and absorb the energy from it. So let's look deeper into this kinetic and potential energy conversions. As we said, kinetic energy is the energy of motion. When something is moving, it must have kinetic energy. Potential energy is stored energy. Let's just make sure we get those straight before we move forward. Some examples of gravitational potential energy are like this bridge. This bridge is above the ground, and if some piece of it was to fall off, it would gain speed as it fell to the ground. A waterfall also is a great example of potential energy. The water starts higher off the ground, and it picks up speed as it falls down the waterfall. Anything falling, such as a snowflake, also has gravitational potential energy until it hits the ground. We can also try to estimate if potential energy has gained or lost. For example, if you stand on a 3-meter diving board, that's a diving board that's 3 meters off the ground, you have 3 times the gravitational potential energy, which is abbreviated here as GPE, than you would have if you stood on a 1-meter diving board, a diving board that's only 1 meter off the ground. Since you're 3 times as high off the ground, you'll have 3 times as much gravitational potential energy. Let's talk about some kinetic potential energy conversions. One of my favorite sports is basketball. So let's talk about playing basketball. As a basketball player throws the ball into the air, various energy conversions take place, but mainly a conversion between kinetic and potential energy. So let's look at this movement. Initially, the ball is here, leaving the player's hand. This is where it has the most velocity. Right as it leaves your hand, it's got quite a lot of speed. As it travels upward, it's going to slow down. Since it's slowing down, its speed is decreasing, so must its kinetic energy decrease. But if you also see here, the height above the ground is also increasing. So since the height above the ground is increasing, its potential energy must be increasing. The ball will continue to slow until it reaches its highest peak, where the speed of the ball is basically 0. So let's assume it to be 0 for just an instant. And at that moment, the ball is not traveling up or down. It's maximum potential energy, because it's the highest point, it's going to be above the ground, and its lowest kinetic energy because it has 0 speed. The ball is basically not moving for that instant. But just an instant later, it will begin to fall, or some people would say descend, to the ground. As the ball falls, it will speed up towards the ground. It's getting closer to the floor, making its height above the ground smaller, so its potential energy also must be getting smaller. On the way down, the kinetic energy of the ball is increasing, but its potential energy is decreasing. When it gets back to the point which the basketball player released it, it's back to its maximum kinetic energy and its minimum potential energy. What you should notice about this diagram are the 2 places where the ball was lowest is where the ball has the least potential energy and the maximum kinetic energy. As the ball rises, it loses kinetic energy and gains potential energy. The point where it has the minimum kinetic energy is also the point where it has its maximum potential energy. As the ball falls, it loses potential energy because it's getting closer to the ground, but it gains kinetic energy. Now, this part of kinetic to potential energy conversions is most closely associated with the work we're going to be doing in class soon, which is building a roller coaster. Roller coasters work because all the energy is built into the system of the roller coaster. It's brought up or pulled to a really tall hill and then allowed to fall down that hill, changing that potential energy that was stored in the top of the hill into kinetic energy as it goes down the coaster. From that point on, there is no energy entered into the coaster. It is just the potential energy that originally had from the top of the hill being converted back and forth from kinetic to potential energy as the ride goes throughout. Let's look at a more detailed picture of what is going on, energy of the roller coaster. Okay, here's a little applet I found on the. What you're going to see here are a bunch of steps are going to form along this way. They're going to be numbered 1, 2, 3, and so on. This little pie chart is going to show the percentage by parts of it as being potential energy or kinetic energy. The blue part of the pie chart is going to be the kinetic energy, and this sort of reddish color is going to be the potential energy. So let's look as this roller coaster goes through its motion, and then we'll stop it and look at it step by step. So here it goes, it's getting pulled up the hill, it's gaining potential energy, it gets to the top of the hill, it turns to kinetic, goes up to lose a little more. That's really fast. I can barely keep up with it. So let's do it step by step, now that we know what the motion is going to look like. So here we go, the roller coaster is going to step 1. As you see, when it gets to the top of that hill, it has all potential energy. It's not moving. This is just like the basketball when it reaches its maximum height. It has all potential energy. Now what's going to happen as this roller coaster rolls down the hill? Well, let's see as it approaches point 2. As we see, when it gets to the bottom of the hill, it has almost no potential energy left. That's because it's almost as close to the ground as it originally started. But it has a lot of kinetic energy. All that part that was potential has basically been converted into kinetic energy. And if you've ever been on a roller coaster, you know this is where you're traveling really fast. As you're falling down that hill, you gain up a lot of speed and you travel really fast at the bottom of the hill. What's going to happen as it gets to point 3 though? Well, as it's approached point 3, it started to go uphill again, making it farther away from the surface of the earth. And since it's gaining potential energy, it has to lose kinetic energy by energy conservation, right? We can't be creating or destroying energy here. We're just changing it from kinetic to potential and back from potential to kinetic. So as this roller coaster now approaches point 4, I wonder if it's going to have any kinetic energy left. Well, look, it does. And it makes sense, right? If it didn't have kinetic energy, the roller coaster would be stuck there. That wouldn't be that fun of a roller coaster. It'd actually be quite scary. It doesn't have all potential energy because it hasn't reached as high as it was at point 1. If it did, then all of its energy would be potential and it wouldn't have any kinetic, so the roller coaster wouldn't be moving, which I said wouldn't be good for a loop-de-loop. So let's see what happens as it approaches point 5. As it approaches point 5, it's basically lower than it originally was, or at the height that it originally was before point 1. So it has no potential energy left. It just has kinetic energy. You should take a guess now of what's going to happen when it gets to point 6. Is it going to have all potential energy? Is it going to have all kinetic energy? Or is it going to have some of each? Let's take a look. As you see, as it's approached the top of this hill, it's not quite as high as 4, so it doesn't have as much potential energy as point 4 does, and it's certainly not as high as point 1, so it doesn't have as much potential energy, but it still has potential energy because it's higher off the ground than it originally was. And it still has kinetic energy because the sum of kinetic and potential have to equal up to the amount of energy it gained being at the top of this hill. And since it's not to the top of the hill, whatever energy is not in potential has to be in kinetic. Notice this little disclaimer here. It tells us that This little app does not take into consideration the fact that there might be friction. If there was friction, then we'd be losing energy, because that's what friction does. And it's not that we'd be losing it, it's just that when you rub your hands together, that friction takes the motion of your hands and converts it into heat. And that's what would happen here. Both the wheels of the cart and the roller coaster track itself would be heating up. This applet is choosing to neglect that for the sake of us studying the conservation of energy and energy conversions. I hope this clears it up. Make sure you fill out your note sheet, and I'll see you soon.